Hi students, in this video we're going to look at the difference quotient. So by the end of this video you should be able to use the difference quotient to estimate the instantaneous rate of change of a function. So the key thing you have to remember is our formula for gradient. It's also the formula we've been using for average rate of change. Now average rate of change is calculated just as a gradient between 2 points on a function, and the instantaneous rate of change, by contrast, is just the rate of change at one particular moment. Right? So at one particular moment, what is its rate of change? How is this function or how is this quantity changing at this one moment, at this one instant? That's instantaneous rate of change. All right, so the difference quotient, guys, is another way of thinking about how we work out our instantaneous rate of change. Now, what I'm going to do is develop it for you, show you where it comes from, and then after that apply it. So in our previous lesson, we talked about instantaneous rate of change using our gradient formula, which we have here. And that's the formula that we use for our average rate of change. And to find our instantaneous rate of change, we want our 2 points to be very close together. So for our example here, if we want to find the instantaneous gradient at x equals 1, we needed to get a point that was pretty close to x equals 1, and then just find the average rate of change between those two. Now, if we wanted to make it closer, we could make it use an x value of 0.001, for example, and that would give us a y value of 1.002001. But for now, we're just going to use 1.1. But the key idea is if we move these points closer together, if we make this 1.1 into something much closer to 1, we should get something much closer to our instantaneous rate of change. All right, now the difference quotient is just a different way of representing this gradient equation. But to start off, we're just going to make some changes by using function notation rather than the y value notation. So here we're saying y2 is we're calling that our function, or the value of our function at x2, and y1 is our function at x equals 1. So just using our function notation there to get rid of some of our y values, but it's still the same formula, it's still the same thing. And then we're going to work through it and rename our coordinates. So instead of having x1, we're going to have just plain old x. So in this case, the point we're finding our gradient at here, x, and x2, we're going to call x plus h. Now what that means is the y values will then change to be f of x and f of x plus h. Okay, so instead of being x2 and x1 and x2 and x1, we're just going to change for these values. Now here, what does h represent? H just represents this small little increase here. So this length here is our value for h. Just what is our change? How much have we increased our x value by to get to x plus h? And ideally for our instantaneous gradient, we want that value to be really, really small. Now, substituting all these values into our formula, we end up with a gradient, or an average rate of change, as fx plus h. So that's f of x2 minus f of x. That's our f of x1 in our old formula. And then we've got here x2 minus x1. Now looking at this, we can simplify this a little bit further in the denominator, and we have x and minus x cancelling each other out, and we have this formula here, and this is called the difference quotient. It's just another way of representing our gradient formula, especially when it comes to finding rates of change. We've got the function, we've got the value of our function at x, whatever x value we want to find, the function of x plus the function of, so the value of our function at x plus h, a little bit more than x, then h, once again, that distance in between. So that distance there is x, and then here this x value is x plus h. And this helps us find our gradient. It looks a bit different, but the key thing I want you to know is that it's the same formula. Now, this difference quotient can then be used to find the instantaneous gradient by trying to make h as small as possible. And then we can see what our difference quotient is converging to. So what we looked at in the previous lesson is if we made our points really, really close together, it looks as though our gradient or our rate of change is converging to some number. So if we moved our point closer, we'll be converging more and more closely to what the actual instantaneous rate of change is. And so that's what we're going to do with our difference quotient in our example in a minute. We're just going to make h as small as possible and see what sort of value we're converging to. Now, note in our formula that h can't equal 0. Right? If we let h equal 0, that means we end up dividing by 0, which we can't do. Well, graphically speaking, if we make h equal 0, these points are right on top of each other, and we can't find the gradient between 2 points that are right on top of each other. So our h value can't equal 0. So what we're actually thinking about with our instantaneous rate of change is what value are we converging to? What value are we getting really close to as we get closer and closer to h equaling 0? And in mathematical terms, this is called a limit. Now, in our formula for instantaneous rate of change, this is how we express it. We've got our difference quotient here that gives us our rate of change, and then our limit as h approaches 0. This tells us as h gets really, really close to 0, as these dots get really close to being right on top of each other, what is our gradient? What is our rate of change? What are we converging to? And so this little limit out the front is what makes our rate of change instantaneous. Okay, makes it instantaneous. All right, so let's do an example. So we want to find the difference, use the difference quotient to estimate the instantaneous rate of change at the point where x equals 1. On this curve, y equals x squared. All right, so remember our formula. So our gradient or our instantaneous rate of change will be f of x plus h minus f of x over h. And we want h to be as close to 0 as we can make it. Now, we could make it really, really small, but just for easiness sake, I'm going to make it a pretty small number. So we're told that x equals 1. And so that means f of x, or f of 1, f of x is going to be our function at 1, which equals 1 squared, which is 1. Now we're going to say h, let's just say it just equals 0.001. Okay, so a small value of h, close to 0. And that means x plus h is going to be 1.001. Right? So x is 1, x plus h is that. F of x plus h is going to be 1.001 squared. That's our function. And that equals 1.002001. You can just use your calculator to work that out. And then putting all of that into our formula, we get 1.002001, subtract 1, divided by h, which is 0.001. That equals 0.002001. Right? The 1 there and the 1 there just cancel each other out. All divided by 0.001. And that's going to be 2.001. Now, that's not going to be my exact gradient because my h value is not quite 0. But if we do make it closer to 0, it's safe to assume that this gradient here is going to be equal to 2. You can try that. You can actually see that it works by picking a h value that's smaller than 0.001 but I'm telling you the gradient is going to be 2. And we'll see more about why in our next video. But at 1, the instantaneous rate of change looks like it's getting really, really close to 2 from our solution here. Alright, so after watching this video, students, you should be able to use the difference quotient to estimate the instantaneous rate of change of a function.